Consider a series RC circuit that looks something like this. We have a battery, a capacitor, and a resistor, and a switch. And when we close the switch, what's going to happen? It's a DC circuit with a DC battery. What is going to happen? Well, when we first close the switch, charge begins to move, so we have current moving, but the charge really hasn't started to build up on the capacitor yet, so the capacitor doesn't have any voltage. And in general, we have this equation, but when we first close the switch, there's no charge on the capacitor, hence there's no voltage on the capacitor. All the voltage of the battery will reside on the resistor at that moment. So our Q would be 0, V would equal IR, and the current would be its maximum value, which would be the voltage divided by the resistance in the circuit at T equals 0. And from that point on, the current's going to start going down. But our maximum current will be voltage divided by the resistance. Likewise, if the circuit's been closed a while, like infinity, then the capacitor will have charged up to its maximum value. It'll be at its maximum voltage, and in fact no more current will flow in that circuit as the capacitor has shut off the circuit. So there will be no more voltage across the resistor, and all the voltage of the battery will reside on the capacitor at that moment. Taking our equation at this moment, then the current through the circuit would be 0, and at that moment, after the switch has been closed a long time, we'll have our maximum charge on the capacitor, which would be equal to the capacitance times the voltage of the battery. So these are our limits as far as when we first close the switch and when the switch has been closed a very long time. In general, though, our charging equation looks like this from Kirchhoff's voltage rule. The voltage of the battery minus IR minus Q over C equals 0. And if I solve this for the current, I would have the current is equal to the voltage divided by R minus Q divided by R times C. The current is, in fact, the derivative of the charge with respect to time. So I could write this as dq dt, and then finding a common denominator for the two fractions on the right, multiplying the first fraction by C over C, I have C times V minus Q over a common denominator R times C. Sounds good. C times V is just the maximum charge, so I'm going to make that substitution. And I'm also going to call R times C, I'm going to make that a different constant. I'm going to call that tau for reasons to be explained soon. So we have dq dt is equal to Q max minus Q divided by tau. Well, if I make a variable substitution, I'm going to let U equal Q max minus Q, Q max being a constant. So U is going to equal a constant minus my variable Q. That means du would equal a negative dq. And making those substitutions, I would have du dt is equal to negative U over tau, tau being a constant. Or, integrating over U, we would get du over U, separating our variables otherwise. Du over U is equal to negative 1 over tau times dt. We're going to integrate from U naught to U and t from 0 to time t. And we get natural log of U from U naught to U is equal to negative 1 over tau times t from 0 to t. Or natural log of U over U naught is equal to negative 1 over tau times t. I want to get rid of the natural log, so I'm going to set both sides of the equals to the exponential. And so I have U over U naught is equal to the exponential of a negative 1 over tau times t, or U is equal to U naught e to the negative t over tau. Alright, so I'm going to substitute back in for my variable. U is equal to Q max minus Q, and U naught is equal to just Q max. So we have Q max minus Q equals Q max e to negative t over tau. With a little bit of algebra, I have that my charge as a function of time is equal to a constant my maximum charge, CV, times 1 minus e to the negative t over tau. This is my charge for all time in this series RC circuit. Let's see if it reaches our boundary conditions. When I first close the switch at t equals 0, I'm going to have 1 minus e to the 0 power. E to the 0 is 1, so I'm going to have 1 minus 1 in my parentheses, which is 0. And I'll have that there's no charge on the capacitor at t equals 0. When I first close the switch, the capacitor has not developed any charge on it yet. Makes sense. When the switch has been closed a long time, t will be equal to infinity. E to the negative infinity is 0. The exponential function asymptotically approaches 0 as time approaches infinity. So I'll have 1 minus 0 in my parentheses, which is just 1. Q will equal Q max, which makes sense. After I've closed the switch for a long time, the capacitor charges up to its maximum value. So we have our charge as a function of time is equal to our maximum charge, 1 minus e to the negative t over tau. Since the voltage across the capacitor is Q over C, I can divide both sides of this equation by C and get the voltage as a function of time. The voltage across the capacitor is equal to the voltage of the battery, 1 minus e to the negative t over tau. At t equals 0, it's 0. At t equal infinity, it's equal to the voltage of the battery. Makes sense. If I take this top equation and I integrate it as a function of time, the constant will be lost because the derivative of a constant is 0. And then I'm going to end up with a negative 1 times a negative 1 over tau, tau being R times C. So I'll end up with the current. The derivative of the charge with respect to time is the current. And with a little bit of algebra, that comes out to V over R, e to the negative t over tau. V over R is the maximum current, and then I have an exponential and negative e over tau. So when I first close the switch, I'll have a maximum current at t equals 0, and then it will exponentially decline after that. The voltage across the resistor is the current times the resistance. So if I take this current, multiply it by R, I get the voltage of the battery, e to the negative t over tau. So voltage across resistance will be its maximum value, the value of the battery, when I first close the switch, and then it will exponentially decrease after that. Note that if I go back to this charging equation up top, if I go a time equal to a tau, which is RC, then I'll have e to the negative 1, which is 0.368, and in the parentheses I'll have 1 minus 0.368, which is 0.632. In other words, when my charge reaches 63.2% of its final value, I would have gone a time equal to tau, which I'm calling a time constant. So when my time is equal to a time constant, tau, which is RC, then I would have gone 63.2% up on that curve. Same thing with my capacitor voltage. When I go 63.2% up on the capacitor voltage, I have gone a time of 1 time constant. For a discharging capacitor, it's flip the switch, and now all the voltage is starting from the capacitor, discharging through the resistor. It's easy to show, we're not going to show it here, but it's easy to show that our charge as a function of time starts off maximum on the capacitor and then exponentially decreases after that. The voltage on the capacitor starts with the voltage that we started with and exponentially decreases after that. The current, being the charge supplied by the capacitor, is going to go in the opposite direction as it was before, negative V over R, e to negative t over tau. And the voltage across the resistor will be the negative of the voltage across the capacitor at any particular time. That's for a discharging capacitor circuit if I were to flip this switch. We probably won't be doing too much of that, but that's so that you would have that for completeness for that situation. Okay, let's try this out. Consider a series RC circuit for which R is equal to 1 mega ohm, C is equal to 5 microfarads, and the voltage of the battery, the EMF, is 30 volts. Find, first of all, the time constant of this circuit. Well, the time constant is defined to be R times C. So R times C is 1 mega ohm times 5 microfarads, 5 times 10 to the minus 6. The 10 to the 6 and 10 to the minus 6 cancel out, and we have a time constant of 5 seconds. So if I had that circuit, it would take 5 seconds for the voltage across the capacitor to reach 63.2% of its final value. What's the maximum charge on the capacitor after the switch is closed? Well, we know that maximum charge should be equal to C times V, because if the switch is closed a long time, I'll have e to the negative infinity, which is 0. 1 minus 0 is 1. So it's going to be C times V, which will be 5 microfarads times 30 volts, or 150 microcoulombs. If the switch is closed at t equals 0, find the current in the resistor 10 seconds later. Well, the current is equal to the maximum current, e to the negative time over tau. If the time is 10 seconds and tau is 5 seconds, this will be e to the negative 2. And my voltage is 30 volts. My resistor is 10 to the 6 ohms, 1 mega ohm. So this will be 4.06 microamps. That will be the current 10 seconds later, or 2 time constants into the circuit after the switch is closed. Let's try a different problem. A capacitor in an RC circuit is charged to 60% of its maximum value in 0.9 seconds. What is the time constant of this circuit? Well, we know our charge is an exponential type equation. Our charge for all time is our maximum charge, 1 minus e to the negative t over tau. So if after 0.9 seconds we've reached 60% of our maximum value, I can substitute that in for my charge at t equal to 0.9 seconds. So I have 0.6 Q max equals Q max 1 minus e to the negative 0.9 seconds over tau. The Q maxes cancel out, and I have an equation with only one unknown, tau. I can solve this for my time constant, tau. Subtract a 0.6 from both sides, add a e to the negative 0.9 over tau to both sides. So I have e to the negative 0.9 over tau is equal to 1 minus 0.6, or 0.4. Take the natural log of both sides. So negative 0.9 over tau is a natural log of 0.4. Divide by natural log of 0.4 and bring tau over to the right. So my time constant is going to equal a negative 0.9 divided by the natural log of 0.4, and that is 0.982 seconds. So the time constant of this particular circuit is 0.982 seconds. That should get you started on RC circuits. Take a good look at the examples in the problem sets. But your basic approach will be using these exponential equations.